These are kind of getting into application based, what different types of basic methods of machine vision. So one is feature detection. This method's based on contrast detection and used for finding features on a product. Example, presence, absence, and size inspection, flaw, strain inspection, color, uniformity, etc. And you can tell to the right how the camera is set up on the left-hand side, looking at objects going down a conveyor, and you can see that there is actually a backlight on this as well. The red object, red square object is supposed to be a backlight. Also, edge detection. This is mainly used for finding edges in measuring applications, and feature detection that are usually not gray level based. So dimension measurement on positioning and orientation. You can kind of tell that a robot, there's a machine vision camera on the end of a robot, and the robot is moving the camera around to inspect, looks like different areas of wheels. So when we detect pixels of a feature, these pixels must have contrast to its background. So when you're looking at an object, getting contrast is one of the most important things, because this way, if you have better contrast, you'll have better an image, and you'll get more accurate results when looking at your objects and inspecting your objects. The difference between the dark and bright, the better contrast, and the better vision system's able to differentiate them. So a rule of thumb is you want to have a minimum of 20% contrast, and that is typically needed for good differentiation between the features, providing good contrast to your object. And below, this is just a little chart of kind of, you can tell black and white, you have you're going to have the most contrast, and as you get on down the lines, when the grays look similar, you're going to have less and less contrast. So I showed this slide earlier, but this is just kind of reiterate a few things we're getting ready to go over. On the bottom left image is a sample measurement program we were doing. So when you zoom in, so on the middle image, if you zoom in, that would be what the image would look like. And on the big image to the right, that is if you zoom in to the maximum as far as you can go. And you can tell on this image you have 0, 15, 40s, and 65s. So like we went over earlier, complete black is 0, and the 255 is supposed to be a solid white, but I'm not really sure. On my screen it's kind of looking gray, but I think that's due to the background of the template, but it's supposed to be white. So you can tell by in this image to the right, it's kind of showing you when you go from completely black and you go out into gray, how your numbers will go up. And you can take a look at this in the machine vision software. So contrast sensing algorithm, it's able to detect one single pixel with a good contrast. But let's say if this pixel moves half a pixel diagonal, you get the same features now spread over 4 pixels, each having a little part of the original contrast. So you can see you on the left-hand image, you have completely black. It would be a 0 and all 100s around it. But if that moved diagonal, you would have that black image over 4 pixels now, and then see how your numbers kind of went from 0 completely black, and it's now more gray, more grayish white. It would go up to a 75. So what's the smallest size of feature that can be repeatedly detective? So we say that a 2 by 2 pixel feature is always kind of guaranteed to be completely covering at least 1 full pixel. And this is not something that we really get a lot into, but when we're kind of setting our threshold on our application and on our perfectly good image when we start a machine vision application, we can kind of look at these numbers and kind of make a start from what our threshold should be, depending on what kind of feedback we get from the machine vision software. So the most common way for vision software to detect a feature is finding like strain, defect, whatever we're looking for. is finding pixels with certain grade level ranges, like your threshold. So threshold range is set between a lower and upper threshold of the grade level. Bright pixels are defined as pixels from grade level threshold to grade level 100%. Dark pixels, like we went over earlier, are 0. So in the image, you can tell on the left that the lower threshold, the dark, is in the yellow, and on the right, the bright is in the yellow. That's just kind of showing you the difference between dark and bright. And on the image below, when we're checking for the pixels that are dark, yes, your vision software is going to be able to find them, and then we can get to know their gray level and position in the image. So you can see that there's a blue square inside the field of view, and that's our region of interest in the software. So we can evaluate the amount of dark pixels against the bright pixels in the region of interest, and then put a limit to it. So if the amount of dark pixels exceeded this limit on the inspection or on whatever we're looking for, then this will cause the inspection or your object, this will cause it to fail. This is kind of how we go about getting a good pass or a bad fail. So on edge detection, this algorithm, this kind of identifies the points where the image contrast changes sharply. This algorithm measures grade level of each pixel along the region of interest. You can see that on this edge detection, on the left-hand side, it starts out gray. And then when we get into the black part, the gray level line will drop down to 0. And then when we get back into the gray level line profile comes back up, back into black, goes back down to 0, and then back into gray, it goes back up. It looks like it's going back up to a little over 60. So this is kind of how we go about setting our thresholds on objects to set and pass. We want to pass or fail, and this is kind of based on this edge detection right here. Here's that the gray line profile enhanced at a better view. So this obviously it indicates the rate of change. This algorithm compares the value of each pixel along the edge to its neighbor. The greater value indicates a positive gradient, dark to bright. Lesser value indicates a negative, bright to dark. And you can tell the differences in these two lines kind of indicates the steepness of the gradient. And as you could tell in the previous slide, how the gradient line profile changed, and it will change depending on whatever object you're looking at. So there's an algorithm for edge detection. It usually works with plus or minus 1 pixel. And sub-pixeling algorithm, the accuracies plus or minus 1/20th or 0.05 pixel can be obtained, but plus or minus 0.5 can be achieved as more as a conservative value in a real application with the camera and the optics and the light situation. So the use of telecentric optics and collimated backlight makes high accuracy measuring possible. Using other optics or lighting techniques will influence the accuracy of the system. When you're doing sub-pixeling, honestly, it should really just be considered as insurance. The only true way to know how repeatable a measurement application will be is to actually set up the application, do the optics, lighting, handling of the software, and record the results over several hundred triggers in the same static part. Then you can compare these results of what you got on the information and then go from there. So a lot of times people want to ask about machine vision applications, and you can run the numbers to kind of decide if the application is doable or not. But like I just said, to get repeatability and to know if the application is actually plausible and we can do it, we have to get some parts. We have to test them out. We have to set up the cameras and lightings and go through the software and actually run the test several times and to see if we can get consistent results that meet your application needs. So sub-pixeling, here's just a quick image of sub-pixeling algorithm. Just kind of examines how the gray levels are of the adjacent pixels around the measurement endpoint. This just uses the information to interpolate the location of the actual edge to the fraction of a pixel. Here's maybe a little better view of it. The edge window algorithm collects multiple subpixel samples along the detective edge on both sides of the initial dictation point. This area's along the dictated edge is called the edge window. Now, the size of this window determined by the subpixel settings in the tool, and these settings allow for precise calculation of subpixel edge. So this algorithm generates each subpixel sample by examining an individual line of pixels across the detected edge. So when we're doing edge detection, this is kind of just getting into detail pretty much about what's going on in the software, where you're getting these numbers from, where you're getting a detective edges, your edge windows, and your region of interest. This is also just called best fitting edge. It's just another example of edge detection and what goes into it. Subpixel location of an edge within a single pixel. So you can compare the gray level to the edge pixel to the gray levels on the pixels of either side of it. In the simplified example shown below, the edge's pixels or gray level is a mix of the left-hand pixels gray level and the right-hand pixels gray level. So the proportions of the mix depends on the location in the edge within the edge pixel. So pretty much it's just saying that your gray level and your edges are going to just kind of determine on where your lines are, where your edges are, where your region of interests are, what your pixel counts are. And here's just kind of a algorithm of how you go about looking for your edges on your gray level and your right level. This is really nothing that can we really get into or need to know the numbers of, but these are just kind of some of the numbers and some of the feedback in the machine vision software that we get. This is just kind of where they come from and how we get those numbers.